We're talking about subset select or model selection or subset selection. So model selection in general, we had basically two criteria, which was doing prediction well or doing the selection of the subsets or subset recovery or feature selection well. And we talked extensively about it. And towards the end, I mentioned this idea that once you select a model, if you then try to do some sort of an inference that come like a confidence interval or t-test or an f-test or something like that, these will all be wrong in the sense that none of this would be valid. The easiest way to see it is do this simple experiment, pick a y and pick a bunch of predictors, all independent. So the model is actually null. There's nothing there. And then pick the one predictor that correlates the most with y. For example, we can look at the t-value. And then compute the p-value based on the, yeah.
Like find a number of parameters with a model. So just use the model to be not splitting.
So if you use the full model, it's not just a number, yeah. So if you select the features, yes. Yeah, if you use the full model and if all the assumptions are correct, like the linearity, let's say Gaussianity and stuff, then yeah, what we did is okay. But if you do the selection procedure induces dependence. That's the issue. And then this is a very interesting setting. So for example, here, what will happen is that if you do p-value, look at the p-value, reject based on p-value, you would 60% of the time reject the null. Whereas if it was calibrated, you would do 5%. So this selection procedure induces like a high correlation between the predictor that you select and y. A priori, they were independent. But if you go through a large collection and pick the one that is highly correlated, it will end up being highly correlated. And so when you fit the model, you find that the coefficient is non-zero. And so this is very important to understand. And it's like a subject of a lot of research. But the data splitting would solve it very easily, but you'd lose a little bit of power. Like you have to train on a small subset. But they're trying to have other ways. People have looked at other ways of dealing with this. Any questions about like model selection at all? So I'd encourage you, this is a very important slide in the whole course. If you want to do statistical procedures, you have to understand that this is a problem. Any sort of procedure you do on data implicitly, like to select something or like a selection bias, basically. So in the use there's like dependence that would otherwise not be there. Okay, let me talk about a related idea. So we talked about model selection, which is you try to pick the predictors, a subset of predictors that work well. Today we're going to talk about an alternative approach, which is the regularization. So you regularize the coefficients. And the regularization idea is that you keep all the predictors, but somehow, I mean, in the case of the regularizations that we talk about, you kind of shrink their coefficients continuously using a knob. And that knob would be like a regularization parameter lambda. And that would allow you to achieve certain interesting properties. So the first thing that it will allow you to achieve is we saw, for example, let's say probably lecture 14 if I'm not wrong, the problem, which was the multicollinearity. And that's where a subset of the random, like a subset of predictors are highly correlated. Then we saw, for example, that if you like a covariance matrix of beta hat, and if X transpose X has this eigenvalue decomposition, V is an orthogonal matrix, lambda is diagonal, and then V transpose, you can write the covariance like this. And then the eigenvalues that are small are going to cause this to blow up. So there are certain directions, so the eigenvectors that correspond to those lambdas point to directions in which the corresponding linear combination of betas is highly unstable, or the beta hat is highly unstable, in the sense that you can't estimate that combination of the parameters well. And so there was a solution for this. There we had a kind of solution. What was the solution? What is the easy way to deal with this? Yes. So that's the thing that we want to do today. So, but there was like the easiest thing to do. Yes. Remove some of the predictors. So some of, like if you have two highly correlated predictors, keep one in the model and drop the other. And the model selection kind of the thing that we talked about, subset selection or model selection, tries to do that to some extent. That could improve, for example, this behavior. The other approach is to do regularization, which has the effect of, we'll see, for example, you do ridge, it has the effect of adding a lambda here. So the subset selection would delete like whole columns. Ridge would allow you to, ridge regression will allow you to sort of like smoothly, or like basically dampen this effect, if you want, of bad kind of directions, as we'll see. So we'll talk about the ridge regression, which is like a L2 penalized linear model. And then it's bias variance decomposition. There's a bias variance trade-off. You've seen bias variance decomposition in the context of model selection. We'll see another version of this today. And we'll talk about the choice of lambda. I mean, the bias variance trade-off clearly tells you like there's like how, as you vary lambda, the regularization parameter, how exactly things would change statistically. And then we talk about L1 if we have time, which is the so-called lasso and its features. Okay, so let's talk about ridge. How many people have seen ridge regression? Okay, a couple of people. Okay. Yes, so we already have seen it, I think, in the multicollinearity lecture as well. So the idea is that you add, so if you look at the OLS, if you remember how we derived it, so you had the linear model y is x beta plus epsilon. And then we try to kind of minimize the error. So you find beta such that y minus x beta, the norm squared, is minimized. In the OLS now, you just add a bit of penalty. So penalize the norm of lambda, so beta. This norm without any subscript is really the L2 norm. J from 1 to p beta j squared. And I should say that here we're going to assume that there's no intercept in the model for simplicity. So no intercept in the model, because generally you don't want to penalize the intercept. There are easy ways to deal with the intercept, as you have seen potentially in the homework problem. So you can center your variables, and effectively you're basically, if you do a regression with intercept with the centered predictors, it would pick up the average of y's, and so you can subtract basically that from y. Basically center everything. You can do a no intercept regression. That would be easier. Then I don't have to worry about like penalizing just the predictors and not the intercept. So we penalize everything. So beta here would be like p-dimensional. And this would be n by p. You can figure out if there is an intercept, you can just, this part just would include everything except the intercept. This is a little bit cleaner to work with for this lecture. So the L2 norm is just the square, the square root of the sum of this, the coefficient squared, okay? And we square it, so this is really lambda j from 1 to p beta j squared, okay? Hopefully by the end of this lecture, you would see like why this is interesting. Okay, so this would give me a solution which will depend on lambda. We call this beta hat lambda. And it happens that for this problem, we can actually solve in closed form. So how do we solve in closed form? Anyone? Can I write down beta hats? Yeah.
This R, for thing, it'd be like assuming because like R min or y minus x, it'll be like b squared minus plus lambda b squared.
Are you trying to just tell what the... So argmin is just saying minimize this function, take the minimizer. So how do I minimize this function? That's the question. Whether it's close to least squares or not depends on how large the lambda is. But I want the exact form, and then we'll figure it out. Yes.
We derive the expression to beta, and then
Wait, we do what?
we derive like the argument expression with the technique.
How do I derive it? What do you mean by derive?
Expanding the.
Oh, expanding it. Expanding it would help a little bit, but it would be a quadratic form. You want to like square this one? Is that what you want? We can try to do it, but that would, yeah. Okay, we take the derivative set equal to 0. That was the kind of the, is that the, okay. So this is just a function, right? And the first thing that you would imagine you would do, like set the derivative to 0. If you, it's like a constraint optimization problem. And it will give you a set of stationary equations and that the minimum has to satisfy. It's not necessarily going to be a minimum, but if I want to minimize this, the first instinct, if it's a smooth function, is to set the gradient to 0. Okay, whether you expand it or not will help you determine the gradient, but I'm going to just write down the gradient of this because the gradient of this part is going to be x transpose x beta minus y. So you can like verify this if you, however you want. You can expand it or do it coordinate-wise. It's easy to write it this way because you don't have to worry about the sign. But this turns out to be the gradient. Okay. How about the gradient of the second part? So the gradient would be like additive. So you get plus the lambda times the gradient of this part. What is the gradient of the norm squared? Yes. It would be beta, yes. So to see it, it's just note. I mean, this is a function. Basically, you just have lambda beta 1 squared plus beta 2 squared plus beta p squared. And so the gradient would be, it's like a vector that has partial derivatives. So the first coordinate would be the partial derivative of this with respect to beta 1, which would be just 2 beta, like lambda is here, 2 beta 1. I was thinking there's going to be 2 actually. So 2 would be everywhere. So 2 beta 1, 2 beta 2. It's good to write it down because then you realize you may miss some coefficient. So 2 beta p. So it will be 2 lambda beta p. And because and this is also quadratic, there's going to be 2 here as well. So I set this equal to 0. Okay, and then I can cancel the 2's, and then I rearrange or basically collect everything into like that has a beta in it. So you get 2. This I can write as lambda I times beta, right? So I get 2, not 2, like lambda I, and then I get a beta here equal to x transpose y. This is like the normal equations for regression, if you remember. But we just have this extra lambda I here. This extra lambda I is very useful because then it would guarantee that this matrix is invertible always. If lambda is positive, this is going to be always invertible. So I get beta is equal to x transpose x plus lambda I inverse times x transpose y. And now we can call this beta hat lambda. Okay, that would be the closed form solution for ridge. So you can already see the advantage of the ridge regression. Even if this is singular, whenever you add lambda I, if lambda is positive, it's going to be invertible. Okay. It's also called Tikhonov regularization. It's very useful in general in linear algebra. When you try to invert a matrix, you might want to add a little bit, tiny bit of I to it, because then this would be invertible and numerically would be more stable. Yes.
assuming for y it's xb and not xb plus error, because it's the definition again.
No. So you're saying y is equal to x beta?
I'll see where the error thing, see from like the derivative stuff to where you're factoring out and you get lambda I. I'm assuming you get the xb and the x functions in x become identity matrix. I don't see where I guess the lambda is there.
No. So this is a very good point to try to understand. So this optimization has nothing to do necessarily with the model. I'm motivating it with the model, but you can write this down. Y could be anything. It's like there's no reason why. If y was equal to x beta, I mean, it can be equal to x beta for all betas, right? So this is an optimization problem. So you have a y, you have an x, and then this is an optimization variable, right? And as I varied, there are some betas that might be like cause y being equal to x beta. That doesn't happen if n is bigger. Then some betas that doesn't happen. That just doesn't happen. If n is bigger than p, it generally is not possible for y to be written exactly as x beta unless y is in the image of x. The part that when I write it like this, usually if you want to be very careful, I usually assume that y is equal to x beta star for some true beta star plus epsilon. Okay, and then I do statistical analysis. But for this, I mean, and I also like motivate why I want to look at this because there's going to be an error. This is a generative model. I'm assuming that y is generated like this, but it may or may not be actually like this. This optimization problem makes sense even if y is not generated like that. And in general, as you vary beta, both these terms would vary. May or may not be zero. And then just take the derivative so equal to zero. That's, yeah.
Where do you go for the two lambda d?
So there's a 2 actually for both, so you can drop them because the other side is 0. You just, yeah, divide both sides by 2. Okay. Yes.
Maybe I missed it, but why does having the identity matrix make it clear that it's
Invertible. We'll see. Okay. Yes. Yeah. Hopefully by the end it will become clear. It's like a fact of linear algebra, but I'm going to tell you, I mean, let's go down a little bit. And if you have the question by the end, we'll try to come back. Any other questions? Okay, so we have this closed form. And you can see if I set lambda equal to 0, you get back the formula for OLS. So you can double check that it like, actually matches that corner case. Always invertible, as I mentioned. So even if you have extreme, like exact multicollinearity, this is singular, this is still well defined. That's the first indication that this is something interesting. There's a constraint form equivalent, sort of. Instead of penalizing, you can add it like as it as a constraint here. By Lagrange duality, there is going to be, for every t, there's going to be a lambda, or for every lambda, basically, there's going to be a t that the solutions would be equivalent or like the same. But I don't want to dwell too much on it. There's a problem with this is that this could be this is always like strongly convex. This objective is going to be not necessarily strongly convex, but the fact that they're dual and they're equivalent is like a fact of convex optimization, which I'm not going to spend too much time. Okay, so you can potentially solve this for a particular t, and it would correspond to the ridge for some lambda. Just worth noting. Now, okay, let's try to analyze this estimator. The first thing that I want to do is connect it back to the OLS. And to do this, we will do, so we have X transpose X, which is V lambda V transpose. And I can write this in this fashion as well. So if you remember, V is like a vector, a matrix of eigenvectors. So the columns are the eigenvectors. Lambda is a diagonal matrix of eigenvalues. And another way of writing that V lambda V transpose, I probably have seen it at some point in the lectures, maybe in the multicollinearity, is like this. I'm not going to use this for much, so that's that. The only thing that I'm going to use is you can write beta hat, because this form a, so V1 up to Vp. For any symmetric matrix, there's an orthonormal, or the EVD would give you an orthonormal basis of the space, that are eigenvectors of. So an orthonormal basis of the Rp, in this case, from the eigenvectors of the matrix. So this is an orthonormal basis of Rp. So I can write every vector in Rp as a linear combination of these. In particular, beta hat is a vector in Rp. I can write it as a linear combination of these vectors. So there's going to be some coefficients there. And it's easy to see. And the fact that I can do it actually uniquely like this is that because that's a basis. The fact that it's orthonormal allows me to actually recover these coefficients as well. These going to be, if I multiply, for example, if I multiply Vk, I know that there's a representation like this. If I multiply by Vk both sides, Vk transpose beta hat would give me Ck times Vk transpose Vk, because Vk is orthogonal to every other vector, so all the terms would be 0 except the one that has Vk. And this would be 1 because that's the normal part. Orthonormal means that these have unit norms, so this would be 1. So C hat k would be really Vk transpose beta hat. But this is also not quite as important. It's just that beta hat has this expression. Then I'm not going to prove this result. We'll prove something more interesting. But then you can write beta hat lambda, the formula above. You can show that it can be written. This one will have also an expansion in terms of Vk, because it's another vector in Rp. It turns out that the coefficients would be just the coefficients of OLS, but scaled down. So you get this extra factor. Once I write the beta hat lambda as an expansion in this eigenvector basis, you get the same coefficients as the OLS, but now we also get this factor. The factor is lambda k divided by lambda k plus lambda. It's always less than or equal to 1. And so it shows you that it shrinks. The ridge shrinks the coefficients of beta hat. If lambda k is large, so what would be this close to? Let's say lambda k is too large. This prefactor would be close to 1. So for those, basically for those directions where lambda k is large, the coefficient is not going to change. But if lambda k is very small, this is going to shrink a lot. So lambda k is close to 0, this is going to be 0. So it would kill the coefficients of the OLS which are in those directions. And those are the bad directions that cause high variance. So this is effectively keep the coefficients that are in good directions, the directions of large lambda. We know that in those directions the variance is small. And in the directions that for which the lambda is small, we know that those are high variance directions from the analysis that we did before. So this shrinking those directions. And so you get an estimator which you can hope that overall will have a smaller variance, as we'll see. Okay, shrinks selectively in certain directions. So to prove this, you need something that I didn't talk about. So it's in the notes if you want that I posted. So we need like the SVD. How many people know the SVD? Singular value. Okay. So like you have seen the EVDs. This SVD would be like, if you have X, a general X, you would have like U sigma V transpose. This is for a rectangular matrix. So U would be orthogonal, sigma would be diagonal, V would be orthogonal. So this is a general, like a generalization, let's say, of EVD if you want. If you have this, then, for example, you can show that if you do X transpose X, because U is orthogonal, you get V lambda would be sigma squared, basically, V transpose. So that EVD follows from the SVD in a sense. But for the subsequent analysis, you just need the EVD, because I didn't talk too much about SVD. I don't want to do it. But if you do the SVD, you can like do this expansion easily. So if you know what SVD is, just check the notes. And the other issue with this is that beta hat might not exist. So this only is useful if there is actually a beta hat. So if X transpose X is singular, technically there is no beta hat. And so this doesn't really make sense. The ridge itself makes sense, but this expansion only works if there is a beta hat. So it works like assuming X transpose X is non-singular. So for that reason, I don't want to spend too much time on it, but this gives you a very interesting geometric picture of the relation between beta hat and OLS. Sorry, the ridge. Okay, so it's like it takes the expansion of the beta hat and it just keeps the coefficients that are good in the directions and then shrinks the ones that are bad. So far, so good. Okay, so that's one view. And okay, the other one is that you can see like basically we are like inflating this. The lambda here is gonna do a good job here. So if you increase lambda, you're gonna dampen more. So the ones that even the larger ones are gonna go down. Yes.
It's like bias. Where's the blend defined? Or like
Where's the lambda is defined here? So lambda is
it's from the ridge regression.
yes, lambda is the regularization parameter. This is important to remember, right? So this is gonna come up, and this is our knob. Basically, we're gonna vary this and study what happens as we vary lambda. Okay, and you can also see it's like I'm explicitly writing beta hat lambda to emphasize that you get a sequence. The ridge is not a single estimate. It's just basically like a continuous path. We'll see. It gives you a sequence of estimators. Okay, I mean, everything that I want to talk about, like, let's ignore the degree of freedom for now. Everything we want to talk about is going to have, like, you'd see once we do this bias-variance decomposition. So let's study the statistical properties. So that would tell you exactly what happens. Let's assume that we have the true regression. Now beta here is going to be true. I would write beta star, but for simplicity, this is the true model. So we have this data generating model, and then we have the E1 assumption. If you recall, the expectation of the noise is 0, covariance of the noise is sigma squared I, and hopefully this should be clear that this would imply that expectation of y is x beta, covariance of y is sigma squared I. So we have seen this before. Okay, so I'm going to do a similar analysis that we did for the OLS. We can compute the bias and we can compute the covariance. And then I'm going to go a little bit further and I can actually calculate the MSE, which we have seen before in model selection, but we're going to do it for the beta hat. So what is the bias? Anyone remembers what the bias of an estimator is? Yes. I'm talking about like a general. So mu hat.
I was defining part of that.
Yeah, so I'm talking about like the bias of a general estimator. So if you have mu hat, let's say, okay, so this would give you just, it's worth pointing out that the ridge would give you an estimate of the mu hat. Mu hat would be an estimate of mu, which would just be x beta hat lambda. And I posted as a homework problem. You can try to come up with, we'll see. I mean, like for example, you can compute the MSE in this sense. So expectation of mu hat minus mu squared. Okay. What I'm going to do in this lecture is going to do MSE for beta. So we can look at beta hat lambda minus beta squared and take the expectation. This is also a good way of seeing how close beta hat is to beta. Okay. So this is trying to say how close mu hat is to mu. Mu hat lambda is an estimator of mu. Same thing for beta. Beta hat is an estimate of beta. I can say how close it is to beta. I can look at the error squared and take the expectation. This tells me on average how close I am. Okay, it's a measure of error. This would be a prediction kind of error. This would be like a basically parameter estimation error. Okay, so the target for this lecture would be this. And we'll see, I mean, if you have already maybe noticed from the last lecture that the MSE, so this would be MSE of beta. I'm going to call this MSE lambda. This is also an MSE, but for a different estimator. MSE lambda would depend both on the bias and the variance of an estimator. There's this bias-variance decomposition, basically. We'll see MSE basically is bias squared plus variance. This has this general decomposition for a generic estimate. But we already know the bias and the covariance. So I'm going to start from that and then show you this bias-variance decomposition. So what is the bias? You've seen the bias. What do you mean when you say like an estimator is biased or unbiased? Just remember, what is the definition of the bias of an estimator? Anyone? Yes?
Expectation of estimators.
Yeah, so it's unbiased if the expectation is equal to what you're trying to estimate. In general, the bias is the difference. So if I have the expectation of beta hat, and if I'm trying to estimate beta, if I subtract beta, that's the bias. If it turns out to be 0, it will be unbiased. Ridge turns out to be not unbiased, so it would be biased. So we just want to calculate the bias. The bias is how much, on average, we are off. Okay, the expectation is away from beta. So in order to do that, I'm going to just calculate, let me just calculate the first term, so the expectation. So how do we calculate the expectation of beta hat? I'm going to write the formula, just x transpose x plus lambda I inverse x transpose y. So I'm just plugging in what beta hat is. So how do I calculate this? Yes.
You move the linear operator to the outside, that's just that times expectation or y.
Yes. Great. Yeah, so this is a fixed matrix. It's linear. And expectation sort of moves past linear operators, so it goes inside. Basically, I can say, I can pull this matrix out. Expectation like gets applied to E of y. Okay, so this comes all out of the expectation, right? And so what is expectation of y? X beta, right? So that's the bias. So you notice, oh, sorry, that's not the bias. So I have to subtract beta. Here's a trick. I mean, at this point, it's fine. You can just report this minus beta, but there's a little trick that we can do here. I can write it in a form which is going to be a little bit more conducive to analysis. So this is the form that I have now. Is there a trick? Yes. Turn into I? How? No. This can't be I. That would be really too easy. Yes. Yes. So this can't be I because that would be orthogonal design. In very special cases, that would be I. So this X is the design matrix. So V, maybe you're confusing it with V. V transpose V would be. So, right?
Oh, I see.
So if X is V lambda V transpose, we'll see a lot of that. So if you see V transpose V, it would be I. But X transpose X is not. Yeah, but the trick is exactly as was pointed out. So you just add and subtract lambda. So let's do it here. I have this. I'm just going to add lambda and subtract lambda I. Okay. Why is this useful? Yes. So you basically separate it into, I mean, and I'm going to multiply the first, I mean, this gets multiplied by the first term and it gives me I because it's the same matrix inverse. And then the other one gives me minus lambda times X transpose, X plus lambda I inverse. And then I get beta. Okay. So that's this matrix times the second term. Right. Now, why this is useful, because if I write down the kind of the, what is called, my bias would be this minus beta. When I subtract beta, you can see this term is just beta. This goes away. So I'm just left with the second term. So you get minus lambda X transpose X plus lambda I inverse beta. So that's the bias of the ridge. So it matches this expression that we have above here. Okay, it's just a simplification. Yes, any questions? No. Okay. So far, so good. It's still ugly, but we'll simplify further later. Let's do the covariance. So how do I calculate the covariance of beta at lambda? Again, same business. You get covariance of, let's call this, let's say A lambda, because that's going to be a messy thing. So A lambda. Okay, so read is really A lambda times Y. You can see it's a linear estimator. Okay, and hopefully everyone knows how to calculate this. A is a fixed matrix. So this formula you've seen many times now. So covariance of A lambda Y would be A lambda covariance of Y, A lambda trans. Okay, and this is just sigma squared I. And so you get sigma squared A lambda transpose. And if you plug in, you get a very ugly formula. So you get X transpose X plus lambda I inverse. There's this X transpose, that's A. And then transpose of A, you get X. And then you get X transpose X plus lambda I. And you have a sigma squared as well. So that's the covariance matrix of the rich estimator. Okay. Not very good looking and not very informative at this in this form, right? But then there it is. Okay. This matches what I have above here. Okay. Questions? Okay, so now what I want to do is I want to do a bit of simplification. Anyone guess what kind of simplification we want to do? How can I simplify these horrible expressions? So, anyone? The key is like the EVD, like eigenvalue decomposition. And so you will see how powerful eigenvalue decomposition is. So we have X transpose X. It's a symmetric matrix. It has an eigenvalue decomposition. Let's say it's V lambda V trans, okay? The first thing that I can ask is what is the eigenvalue decomposition X transpose X plus lambda I? This is another symmetric matrix. And yes.
Since lambda I is just the eigenvectors along the diagonal matrix, would that be like, I guess you could factor out the diagonal matrix of V transpose V transpose.
Yes, you're on the right hand. So I can write this as, so this is V lambda V transpose. I can write it as V V transpose, let's say. Okay.
I guess that they could maybe factor out that.
Okay, so I'm gonna do this. Let's see if you agree. I can write it like this. Does that look good? So V lambda V transpose, I have V lambda I V transpose. Okay. And then it wouldn't be two. So this is good. Now what I'm gonna do is I can pull out, basically you can factor out this. Let me write it down and then see if you agree. So I can pull these from both sides out. Okay. So this is I, right? So I replace the I with VV transpose because that's an orthogonal matrix. And then so you can verify this is just basically lambda I. And then I'm pulling like V from this side, V transpose from that side. So if you multiply, you can convince yourself. Yes.
Why diagonal lambda I is not the same as the I guess eigenvalue matrix? Is it because we're not assuming the eigenvalue matrix has off diagonal equal to 0?
No, it's off diagonal is 0. So this is, the eigenvalues are different. So this is like this. Lambda I is just lambda. Yeah. So what happens is this is a diagonal matrix, with diagonals being lambda 1 plus lambda, lambda 2 plus lambda, lambda p plus lambda. Not sure I understand. So what was that?
So I does one out for the diagonal matrix separate plane and for each step.
Yes, they're not the same because of exactly that. But when you add them up, you just get another diagonal matrix, which has this form. So this is the eigenvalue decomposition of this matrix. Why? Because it's of that form. You have an orthogonal matrix V, a diagonal matrix in between, and then V transpose. So this simultaneously shows multiple things. One is that when I add like a diagonal matrix to, like a multiple diagonal matrix to a symmetric matrix, it doesn't change the eigenvectors. And it only shifts the eigenvalues by that amount. Okay, and then you can also see here why this is always going to be invertible. Why is this going to be always invertible? So you can read it in the eigenvalues. So this matrix would be invertible if that diagonal matrix is invertible. And that would be invertible because like the diagonals would be at least lambda. Right? So let's say we know that x transpose x is positive semi-definite, so these are all non-negative. Okay, lambda, if lambda is positive, even if some of the lambda i's are 0, then that would compensate, like you get lambda. Okay. In particular, x transpose x plus lambda I, this inverse is also going to be, once you have the eigen decomposition, the operations basically apply to the inner matrix. So this would be like V lambda plus lambda I inverse V transpose. This you can verify easily that this is really the inverse by multiplying the two matrices. Okay, so the inverse would be applied to the inner diagonal matrix. Okay. If I square this matrix, it would just be applied to the diagonal as well. Polynomials would just apply to this. Okay. So far, so good. So let's see. I can, for example, simplify this now that we have this here. So I get expectation of beta hat lambda minus beta is equal to, you get a lambda here, and then you get V, and then you get lambda transpose. Sorry, lambda plus lambda I inverse V transpose beta. Okay. And I can move it inside this as well if you want. This is going to be negative. You can write it like this. This lambda, I can write it as lambda I and move it inside. It just doesn't matter. So this whole thing is a diagonal matrix. And it's just going to be a diagonal matrix with these elements. So lambda times lambda I plus lambda inverse. In other words, it would be lambda divided by lambda I plus lambda. So then you multiply diagonal matrices as if you're multiplying the scalars. Okay? So this is going to give you a very simple formula for beta. So you get the V, this diagonal matrix, and then V transpose beta. Okay? Sounds good. Questions? I'm just rewriting this in this fashion. Okay? Yes?
I guess pattern we should notice for like simplifying this equation, if we see like a bunch of like diagonal matrices, this turns into
It's just, yeah, diagonal matrices act like numbers. Like if you just do multiplication and division, it's just, you can just take this, the general term and just multiply. So if you do like, yes, yeah, just multiplying multiple diagonal matrices is just a single diagonal matrix. And then the operations are basically pointwise. Okay, that's the power of diagonalization. That's the power of EVD. So let's do covariance. Covariance of beta hat lambda. Let me copy paste this horrible looking expression. So we have this. Copy, paste. So what do I get? If I do the same procedure, I get sigma squared. This is going to be V lambda plus lambda I V inverse. Sorry, V transpose. This is inverse here on the diagonal. V transpose, that's the first term. This one would be V lambda V transpose. This one would be This should be inverse. I'm just missing another inverse here. It's the same thing transpose, but it's, so this thing would be V lambda plus lambda I, inverse V transpose. Okay, and then some simplifications happen. V transpose V is identity. This is identity. And so you can see just a giant diagonal matrix in between. Okay, so you get lambda plus lambda I inverse, lambda, lambda plus lambda I inverse, V transpose. Okay, and this is a diagonal matrix. Can anyone tell me what the general diagonal element is? Let's see if you, yes. Just replace these with lambda I, this with lambda, and see if you can read what it looks like. Anyone? Just three diagonal matrices, and then you just read off the diagonal elements. This is like lambda I plus lambda inverse. This is lambda I, and then lambda I plus lambda. Which, yes?
It would be lambda I divided by lambda plus lambda I squared.
Yes, let me write it like this. Lambda I plus lambda squared. Exactly would be this, right? You just treat them as just numbers. Imagine this is just looking at the ith entry, will be lambda I plus lambda, and then inverse would be 1 over that because it's diagonal. And then this will be lambda I. So this goes to the numerator, and this is the same thing in the denominator, so you get the square. So here is going to be V transpose. So you can see all these matrices are basically diagonalizable by V. The same basis diagonalize everything. So these commute with each other in the sense that, so you can basically treat them as diagonal. When I'm just map to this V space and just work with diagonal matrices. So this is really the power of the eigenvalue decomposition. So all these matrices kind of have the same eigenbasis, diagonalizable by the same eigenbasis, and so we're going to use these expressions. So this is the simplified expression for the bias, and that's for the covariance matrix. Now let me try to compute what I advertised. Any questions about this? Maybe pause a little bit. So the whole thing is that you start from the eigenvalue decomposition of this. You argue that this matrix has the same eigenvectors, basically diagonalizable by V, and then you figure out what the diagonal kind of entries are. Basically, those are the eigenvalues, and then you plug in, and then everything kind of would be in the simplified diagonal sense, which you'll see is going to be very helpful. So let me try to complete my advertisement. So I'm going to look at the MSE. This is the measure that's very useful to see how well the estimator is predicting, or how close, basically, my estimator is to. This is a measure of error, average error of the estimator. Right? So this has a bias variance decomposition. How do I arrive at that? Anyone remembers? I mentioned briefly a trick that you would do. You add and subtract something. What is that something? No, so let's say this is an estimator. I'm going to add its expectation, or subtract its expectation and add its expectation. This allows me to create the bias term. So this, if I add and subtract, you can see this is the bias. Okay, I'm going to call this the bias. It's a vector, which we already calculated. And this is deviation of beta hat from its expectation. It's related to the variance. Okay, I'm going to square these, and you'll see. So when I square, I get expectation. The first term would be norm beta hat minus expectation of beta hat squared, plus the second term would be bias squared. I'm going to write it like this. And then I get twice the first term transpose this deviation transpose times the bias. Okay. Okay. The expectation applied to the first one, I'm going to leave. And then the second term is deterministic. So the expectation doesn't do anything to it. It's just going to be itself plus twice the expectation of this term. Okay? And something happens to that expectation. That's a cross term. What happens to cross terms in lower division courses? In statistics? 0. Like, it's a good guess, like 99% of the time it's going to be 0 if you did it right. So why is this 0? So the bias comes out, the bias is constant, comes out. So you get expectation of, let's say, beta hat lambda minus the expectation of beta hat lambda transpose, and then the bias goes out because it's constant. By linearity or expectation, I can pull it out. And then the expectation also goes inside the transpose. Transpose is also a linear operator, so you get expectation beta hat lambda minus expectation beta hat lambda. And then at this point, you can see y is 0. Okay? Something minus itself is 0. Basically, the expectation moves past everything, goes applied to this minus this, would 0 this out. Okay, so this term is 0. This term we already kind of have a handle on. You can see it's bias squared, and so if my advertisement was correct, this would be like variance squared, and it's really a variance squared. But if you think about it, it's just the sum of the variance of the elements of beta hat. But we can make it a little more clear. Is this so far okay? Yes.
Left-sided. Have like the bias at lambda minus e bias at. How is that different from the right side? How you do in the set of expectation of like a constant is the constant. So why is the left side not 0?
Which one is the left side? What are you talking about?
Left side. Oh, it looks the same.
Oh, you mean this one?
Yeah, why is that?
So anyone can tell me why this is different from this? There's a big difference here. So this is nonlinear, so this is a norm here. So the expectation cannot move inside the norm square. Okay. Transpose is linear. It moves in. Yes. That's the main. Yeah. Otherwise, remember they have like the variance of a vector is like this. If it was possible to move it, every vector would have, like every random way would have a 0 variance. It can't move through. Right? Good question. So, and then points out to the fact that I should do this as well. So this is also a vector. I should do it like this. Bias is a vector, so the first term is like squared norm. The second is also squared norm. Any other questions? Maybe let me try to clean this up a little bit. This would be norm beta hat lambda minus the expectation of beta hat lambda, norm squared. So this term is a notion of a variance. It's actually the sum of the variances. So I want to kind of simplify this a little bit, or like I want to connect it basically to the covariance of beta hat lambda. It can be computed based on the covariance. Right. So what I'm going to do is I'm going to, for simplicity, call this deviation. Let's say z lambda, for simplicity. So I want to ask you, anyone remembers what the definition of the covariance of beta hat lambda was? Can I write it in terms of the z lambda, let's say? The very first lecture when we defined the covariance matrix, what is the definition? Anyone?
So we sigma squared, then you have the ground matrix, but the ground matrix for lambda.
No, I'm not talking about the general. I'm gonna give you a random vector, and I wanna write down the definition of the covariance matrix. Let's do that, then try to calculate. What will be the definition? Yes.
Take the value of beta and then that thing times by beta hat lambda minus the expected value of beta hat lambda transport.
Let me, because there's too many lambdas. So let's say I have a random variable y. I want to compute the covariance of y, like say a random vector. What would be?
Minus by expected values of y, that whole thing times by y minus by expected value of y transport.
Okay, yeah, I'm assuming you mean something like this. Yes, so y minus the expected value of y. This is the centered version. That's what I call actually z. And this is, or in that lecture that we had, we called this y tilde. And then the same thing transpose. So you get the expectation of centered vector times itself transpose. That's the definition. Right? So I call this z, so this is going to be z lambda transpose. So beta hat lambda minus its expectation is the centered version. That vector times its transpose, the expectation. Okay, that's what I was looking for. This is the definition of covariance matrix. It's close to what we want. So what we want is really expectation of z lambda norm squared, which I can write as expectation of z lambda transpose z lambda. And we look at the covariance matrix, it's like almost there, but it's switched. So expectation of z lambda transpose. This is a matrix, that's a scalar. So how do I relate these two? There's another trick here, which we talked about, known as the trace trick. What is the trace trick? It's all sort of like, this course is all tricks. You end up being a magician by the end. Yeah. Yeah.
Expectation is just a constant number, we can let the trace to it, the trace equal to it. And then you could use this to
Okay, so we can't just, I can take the trace of both sides. I can't just apply, trace is going to do something destructive, but I'm going to take the trace of both, let's say. I'm going to take the trace of both sides. This I can do. Yeah, okay. Let's see what happens. Next, what should I do? Trace is linear, right? So
This is equivalent to trace expectation z lambda transpose z.
yes, but if you want to do it properly, first I'm going to switch the order because they commute. So trace is a linear operator, expectation is linear, so they commute. So first expect trace goes in, then trace has this property, like cyclic invariance. So I can permute cyclically inside the trace and it doesn't change. So I can move this to the other side. And trace, there should be transpose here. So I'm going to move this to the other side. You get trace of z lambda transpose z lambda. Okay, this is valid. I switch the order. So now what? Another tricky step. Z transpose z is a scalar. What is the trace of a scalar? It is itself. It's like a 1-by-1 matrix, so I can just drop the trace. I get z lambda transpose z lambda, which is really what I wanted. Okay. So we notice that this term that we were looking for or after is like trace of covariance of beta hat lambda. Okay, so and you know what the trace does? It just sums the diagonal entries. Right? So the diagonal entries of the covariance are just the variances. So this term is really the sum of the variances of the coefficients of beta hat. Good? So this is called the trace trick, another manifestation of trace trick. Okay? So once the dust settles, we prove this result that MSE lambda is bias squared, or something like this, plus the variance. Variance is the trace of the covariance beta hat. Now, we still have some time, like something to do. I'm going to plug in. So if you look at the expressions, I'm going to apply the result here. So let's do it here because it's clear here. So I'm going to look at this guy first. So this is the bias squared. So bias squared would be norm V, this diagonal matrix, V transpose beta. And so the first V I can drop. This you can easily prove for yourself. Then you take the norm of V times something, the V goes away. It's like the L2 norm is unitarily invariant. The way to do it is just transpose. This vector, like this vector times it's like transpose of it times itself that kills the V. Say diagonal lambda lambda I plus lambda V transpose beta. I'm going to call this alpha. This is really an expansion. If you write it down, it would be V1 transpose beta up to V transpose. So this just collects the coefficients of beta in the basis of the eigenvectors. And so this is a diagonal matrix times alpha. What it does is just entry-wise gets multiplied by. Yeah, okay. Let's go. So with this, okay, now I need to do it here. Just a little here. Sorry, just too much. Just remove this. Maybe it's easier to remove this thing. Okay, so now I'm going to do the trace of covariance of beta hat lambda. So what happens here? Another application of the invariance of the trace to cyclic transform. So you get like this, V, there's a diagonal term here, and V transpose. Right? So what can I do here? Move things around. I'm going to move this closer to this guy. It has to be cyclic. And then V transpose V would be I. So I can just drop. I get the trace of diagonal lambda I plus lambda squared. And so the trace of a diagonal matrix is just the sum of the elements. So you get sigma squared summation I from 1 to P lambda I plus lambda. So all this calculations kind of paid off because we got very clean formulas for the bias squared and the variance in terms of the very simple parameters, eigenvalues, this alpha I, and then lambda and sigma squared. Okay, so once the dust settles, you get this very nice decomposition. So the MSE of ridge is bias squared plus variance. And that's exactly what we did above. So if you check, the bias is like alpha I squared lambda I squared divided by that, lambda I plus lambda squared, and the other one is lambda I. So you get, I'm doing K here, but the index doesn't matter. You can rename it. Okay, and so what happens is that at lambda equal to 0, you can see the bias is 0. Any question? At lambda equals 0, the bias is 0 because this is 0. And so you get back this term. This is also going to be actually 0. So you get 1 over lambda k squared. And you can see it's going to be problematic. So you get sigma over k 1 over lambda k. And this could blow up because lambda k's could be small. At lambda to infinity, the variance would be 0 because this is 1 over lambda squared. So asymptotically, it behaves like 1 over lambda squared every term. And so it goes down to 0 very fast. So at infinity, the variance is 0. But this one is going to converge to, the coefficient converge to 1. So you get summation of alpha k squared, which is in fact going to be just the norm of beta squared. And so at the two ends, one of them is 0, the other is non-zero, okay? And so if you look at like the plot is something like this generally. So the variance starts high at 0 and goes down to at infinity to 0. The bias starts 0 at 0 and then goes up to some value at infinity. And then the sum of the two is that red curve, which is the MSE. And you can see it goes down and then goes back up. So there's a minimum. So there's an optimal value. You can pick a lambda. That's the MSE, like that is minimum. Okay, and it beats the OLS because OLS MSE is here. Okay, in the way that I mean, OLS is not always that bad, but this is a high noise situation, and you can see like the unbiased estimator, which is the OLS, is there. The rate is much better in this case. Okay, so what happens here is that you're trading off a little bit of bias. So at this point, the estimator is biased, but it reduced the variance a lot. If I go further, I reduce the variance more, but the bias increases, so it's not worth it. So like at the when you get here, before here, the increase in bias is not as much. Basically the variance is dropping too fast, so it's good. At this point, it's like the optimum, after which the variance is going down, but the bias goes faster, so you're going to stop. So this gives you this result, and then there's this result at 1970 that proves that basically there is always a lambda which is always better than lambda equal to 0, and it's easy to prove by looking at the derivative of the MSE at 0. So you look at this formula, take the derivative with respect to lambda, evaluate at 0, and it turns out to be negative. Okay, so this saying that at this point the derivative is negative, so the function is pointing downward. So it's always good to move away from 0. There's always going to be something. It could be happen at infinity, but like the positive lambda, there's a positive lambda that does beat the OLS. So in other words, there's a bias estimator that beats the blue. If you remember, OLS is the blue, but that's okay because so if you remember, the Gauss-Markov was saying that OLS has some optimality. The optimality was among linear unbiased estimators has the smallest variance. Okay, it is still true. The thing is that among all unbiased estimators, the MSE would be exactly equal to the variance. So among all linear unbiased estimators, this is still best in terms of the MSE, but not among all estimators. Let's say among all linear estimators, Regge is linear as well, and it's biased, but if you enlarge that class, then OLS is not best in terms of the MSE because there's something that adds a little bit here, but removes the variance a lot. Okay, sorry, I can stop, but just maybe yeah, I have a few slides, but maybe you're out of time a little bit. So what you can do is that you can, in practice, so this one, just want to point out, you can plot this if you know alpha, which means you know beta. It has the same flavor as the model selection problem. So we can't plot this. In theory, we can plot, but in practice, you have to approximate it. You can approximate it by cross-validation or use this generalized cross-validation, which because we're out of time, maybe I'm going to come back, talk about this a little bit, and then move on to the lasso. So lasso is, hopefully you have seen it, but we're going to talk a little bit about it. Replaces this with the L1 norm, and then some properties would change. Okay, thank you guys. Let me stop here. Come back next time and continue. Thank you.